This is the 16th video in our series on topology, and we're still working through the notion of compactness. Today we're going to look at another description of what it means for a set to be compact, and we're also going to look at compact sets in the real line. So let's first recall what it means for something to be compact. So a topological space X is compact if every open cover U of X admits a finite subcover. So that means if we've got a collection of open sets where they union to the entire set X, then we are guaranteed to be able to take a finite number of those open sets that also union to X. Now, I want to introduce maybe a dual notion to this notion of an open cover, which is going to turn into something that we can use to also classify compact sets. And well, how are we going to do this? Well, we want to exchange the union for an intersection, which means we'll eventually exchange the openness for closedness. This is kind of the duality between open sets and closed sets, and our ability to define topological notions in terms of open sets or closed sets. But anyway, let's get to it. So a collection of subsets C, so they're subsets of X, so that means this collection is a subset of the power set. Okay, so this collection of subsets is said to have the finite intersection property if, when we take any finite subcollection and take their intersection, we get something that is non-empty. So anyway, that's the finite intersection property. Okay, so now we're ready to tie this into compactness. And so we'll prove that X is compact if every collection of closed subsets C with the finite intersection property has this maybe boosted property that if we take the intersection of all of them, we get something non-empty. And so let's observe that this is kind of the reverse of what we have over here with our open cover. And so for the open cover property, if we have something where the union of all of them is an open cover, then we're guaranteed to have a finite union, which is also a cover. Here it's the opposite. We've got this finite intersection property giving way to this maybe arbitrary intersection property. Okay, so anyway, let's get down to the proof here. So let's suppose that X is compact, so we're doing this forward direction first, and we've got this collection C of subsets of X with the finite intersection property. And so now we want to use the fact that X is compact, so we better get a collection of open sets. And so we can form a collection of open sets out of our collection of closed sets. I guess I should say these are all closed by looking at their complement. Remember, the complement of an open set is a closed set, and the complement of a closed set is an open set. So let's do just that. So let's consider this thing that I'll call U, which will be everything of the form X minus C, as C runs through everything from our collection of closed sets, script C. Okay, so now let's observe that this is going to really bring us into two cases. We're not going to like enumerate them as cases, but the two cases are either U covers all of X or it does not cover all of X. And we'll in fact show that it can't cover all of X. And then the fact that it can't cover all of X will lead us to be able to show that this infinite intersection is in fact non-empty. Okay, so let's get to proving that U cannot cover X, and we'll do this by way of contradiction. So by way of contradiction, let's suppose that U covers X. But if U covers X, then that means it admits a finite subcover. So that means that there exists U1 up to UN inside of U such that U1 union all the way up to UN is equal to X. But now let's observe that UI is equal to X minus CI for let's see, Ci inside of our collection of closed sets. Just by the way that we're building our collection of open sets U up there. Okay, so, well, what does that mean? Well, that means that if we go and take the complement of all of this, we'll have the empty set, which is equal to x minus x, is equal to x minus this union u1 up to un. But then, by the way that set minus distributes over a union from maybe like a basic proof course when you work with sets, you know that this is going to turn into x minus u1 intersected with x minus u2 intersected all the way up with x minus un. But then since the ui's are x minus ci's, the x minus ui's are going to be ci's. So this is going to be C1 union C2 union all the way up to Cn. But let's see, why is that a contradiction? Well, let's observe up here, we supposed that this C had the finite intersection property. But let's go over here and look at the finite intersection property, which says that any finite subcollection has a non-trivial intersection. But look at what we've done right here. We have constructed a finite subcollection that has an empty intersection. And so that's why we got this contradiction right here. And so, well, what did we contradict? Well, we contradicted this ability for U to cover X. So, well, what does that mean? So that means down here we have that U doesn't cover X. But actually, that's going to essentially take us all the way home. So that means that there exists a little x in big X where little x is not inside of the union of all of these U's. Okay, well, that's what it would mean to not cover. It means that if we take the union of everything inside of our collection U, we're going to miss something. But then let's recall that these U's were simply x minus C's, where those C's came from our collection of closed sets. But then if x is not inside of that union, that in fact is equivalent to saying that x is in the intersection of all of these C's as C runs through everything. But let's observe that that actually is exactly what we wanted to show. We started with this finite intersection property for our C's. We use that finite intersection property to show that this complement could not cover all of X. But if that complement did not cover all of X, we saw that that led to being able to find an element that is in the intersection of everything from this collection of closed sets. But if we found something inside of that, then that means that this intersection is non-empty. But that's exactly where we needed to go for this direction. Okay, so now let's move on to the reverse direction. So now let's get going with the reverse direction. Let's notice that we're going to assume all of this stuff over here and then prove that X is compact. Proving X is compact using this definition of compactness over here. So that means we will start by supposing that U is an open cover of X, and then somehow extract from this U a finite subcover. But now U is going to be a collection of open sets. In order to use what we are assuming, we need a collection of closed sets. So let's maybe construct those kind of dual to how we constructed the open sets in the previous direction. So let's set C equal to the complement of everything from U. So again, that's just going to be exactly like this right here. It's going to be everything X minus U as U runs through all of our script U. But now let's get going. So let's observe that since U is an open cover, that means that X can be written as the union over all U in script U of U. Anyway, that's exactly what it takes to be an open cover. But now we can take the complement of both sides of this equation, just pretty similarly to what we did before, and that's going to turn into the intersection over all u in u of x minus u, because we're taking the complement, and observe that that's going to give us the empty set. So let's observe what we have here. We've got the intersection of this arbitrary collection of closed sets. This is an arbitrary collection of closed sets because, check it out, it's a arbitrary collection of complements of open sets and thus closed sets. We've got that is empty. But now let's observe by kind of the contrapositive of this thing right here that we are assuming. That means that there exists a finite subcollection of these closed sets that intersect to something empty as well. So let's write that down. So that means that there exists a u1 up to un such that the intersection of all of those, not all of the u1s, but the x minus u's, so x minus u1 intersect all the way up to x minus un is empty. Now, let's be really careful about why this is the case, why we can go from this step to this step. Well, let's say that this was impossible. Let's say that we could not find this u1 up to un where that finite intersection was empty. Well, if that was impossible to find, that means that our set C would have in fact had the finite intersection property. But then if our set C had the finite intersection property, then we would have guaranteed this arbitrary intersection to be non-empty because of our assumption over here. So since this arbitrary intersection was empty, then that means that our set could in fact not have the finite intersection property. But if it doesn't have the finite intersection property, then we can have finitely many of these u's where their complements intersect to something empty. But anyway, now we're ready to take the last step, which is take the complement of this equation right here. But if we take the complement of that set equation, we're going to get u1 union u2 all the way up to union un equals x. So, well, what does that mean? Well, that means that this u1 up to un is a finite subcover, but that's exactly where we wanted to go. We took an arbitrary open cover and we found a finite subcover, meaning that x is compact. Okay, so now that we've looked at this theorem, we want to look at compact subsets of the real line. All right, so in order to look at compact subspaces of the real line, we need the notion of a bounded set in Rn. And I think you could probably write down the notion of a bounded set in any metric space, but we're just going to focus on Rn. So a set A, which is a subset of Rn, is said to be bounded if there exists some real number m, which is bigger than 0, so that for all x in A, the distance between x and the origin is less than m. So let's observe that that is equivalent to saying that our set A is contained within the ball of radius m centered at the origin. And here's a little picture of that scenario. So let's say that this peach-colored set is our set A. And then, well, notice that we can find this circle centered at the origin that contains our set A. So that's maybe the general geometric way of thinking about this. Okay, so anyway, let's get to our main result of the video, which is proving that a set in the real line is compact if and only if it's closed and bounded. And this inductively will extend to a subset of Rn. So a subset of Rn is compact if and only if it is closed and bounded. And this is in fact the definition of compactness that you might see in a lot of introductory real analysis books. In fact, I think they usually use this definition in the text and then they'll set up the maybe more general definition as a set of exercises. Okay, so anyway, let's get to this result. So we're going to start with the forward direction. So in other words, we'll start by assuming that K is compact. And I guess it goes without saying, but I should be a little bit careful and point out that here we're in the Euclidean or the standard topology on R. And I say that goes without saying because we saw like some really strange things when we looked at other topologies on R. And we definitely saw some places where we had some sets that were not compact, but were definitely bounded. But I guess you need a metric space to be bounded, and we were actually looking at things that were not metrizable, but that's kind of neither here nor there. Okay, so anyway, we've got a compact set in the real line, and now compactness means that every open cover has a finite subcover. So let's take an open cover that will lend us to see that this thing is bounded. So let's notice that U, which is going to be the set of all open intervals of the form minus n to n, as n runs through all natural numbers, is most definitely an open cover. I think that's pretty clear. It's just extending out these intervals a little bit at a time. So since it's an open cover, that means that there exists a finite subcover. But then that finite subcover is going to give us the following scenario. K is contained in this finite union, maybe minus n1 up to n1, unioned all the way up to minus nk up to nk. So that's what a finite subcover would look like. But let's observe that all of these things right here are nested within each other. So minus 1 to 1 is nested inside minus 2 to 2, which is nested inside minus 3 to 3, and so on and so forth. So that means that this union right here is in fact equal to minus m to m, where m is going to be the maximum of this n1 up to nk. But let's notice that K being inside of that interval right there is exactly this condition right here, specified down to the n equals 1 or just the real number line thing. So notice that minus m to m is in fact the ball of radius m centered at 0 in the real line. So in other words, what we have here is K is bounded. Okay. So now that K is bounded, we need to show that it is closed. So let's also note that we can use one of our previous results to prove that immediately. And that is that K is a compact subspace of a Hausdorff space, that Hausdorff space being the real line. But we proved that all compact subspaces of Hausdorff spaces were closed. So that means that we have K is closed. So there we've got it. We've got compact implies closed and bounded. Now let's see the reverse direction. All right, so now for the reverse direction, let's start by supposing that K is closed and bounded. And now we want to end up with K being compact. And let's observe that bounded implies that K is contained within, well, we could write this as minus m to m, just like using our definition of boundedness over there. But now if K is contained within this open interval from minus m to m, it's contained within a slightly expanded closed interval. So we can just take it to be really simple and say that K is contained in the closed interval minus m minus 1 to m plus 1. Okay, nice. So now let's observe that that means that K is a closed subset of a compact set, because we know that this closed interval minus m minus 1 to m plus 1 is compact by some stuff that we did in a previous video. But we also know by a previous result that closed subsets of compact sets were compact. So that means that in fact K is compact as necessary. But let's observe that these proofs were pretty short, but that's because we proved a lot of preparatory results in previous videos. Okay, so now let's look at a nice application of this, which is going to be a generalization of something that you saw in your calculus class. Okay, so the result we're going to look at is really the general, maybe not the most general version, but a general version of the extreme value theorem from calculus. Let's recall that the extreme value theorem said that if you have a function that is continuous on a closed interval, then that function attains its maximum and its minimum on that closed interval. But now if we're going to move to generalize that a bit, we want to exchange closed interval for compact topological space, and that's exactly what we're doing here. So let's suppose that X is a compact topological space, and we have a continuous function from X to R. Now I'd like to point out here that we don't need R to be the codomain. We just really need a topological space with the order topology. Now, I'll let you look up the more general result here if you're interested, but the case with the real numbers is like close enough to what you would see with the ordered topology that I think this is good enough for our purposes. Okay, so anyway, if you've got that set up, then there exists elements of X, which we'll call X0 and X1, so that for all little x and big X, we have f of x0 is less than or equal to f of x, which is less than or equal to f of x1. So let's observe that this f of x0 is in fact the minimum value of our function because everything is bigger than it, or maybe equal to it, equal to or bigger than it. And then this f of x1 is our maximum value. So this is the extreme value theorem. Our function attains its minimum value and its maximum value as long as we've got a continuous function and a compact domain. Okay, so let's get to the proof here. So we know that X is compact, that's our assumption, and we know that F is continuous, that's another one of our assumptions, but that tells us that the image F of X is also compact. So in the previous video, we proved that the continuous image of a compact set was compact. Okay, so well, then F is not only compact, but F is a compact subspace of the real line. But that means that F of X, or the image of X under F, is closed and bounded. So let's get that on the board and we'll start to use that. Okay, so we've got f of x is closed and bounded. But then let's observe that bounded means that it has an upper and a lower bound. But then in the real line, everything with an upper bound and everything with a lower bound has a least upper bound and a greatest lower bound. That's by the completeness of the real numbers. But then since we've got a closed set, that set does not just have a greatest lower bound and a least upper bound, but it also contains the greatest upper bound and the least upper bound by the closedness of this set. That was probably in a homework exercise earlier. So let's set m equal to the infimum of f of x. So that would be the greatest lower bound. We'll use lowercase m here. And we'll set capital M equal to the supremum. So that's the least upper bound of our set f of x. Okay, so anyway, by the completeness of the real numbers, we know that those exist. And then by the closedness of our set f of x, we know that they're inside of this set. So that means that there exists an x0 and an x1 inside of x, such that f of x0 is equal to little m and f of x1 is equal to capital M. But then we're good to go because we know that for all x inside of the domain, f of x has got to be bigger than or equal to the greatest lower bound, which was little m, which was f of x0, and it's got to be less than or equal to the least upper bound. But the least upper bound is capital M, or f of x1. But check it out, we just proved the result that we wanted to prove. Okay, so now I'd like to observe that there's a pretty quick corollary of this, which gets closer to the extreme value theorem from calculus, and that is if we have f from the closed interval a, b to the real numbers being continuous, then we know that the image of this interval is in fact equal to another closed interval. So we could talk our way through this a little bit, but let's notice that the image of this interval, since the interval is compact, the image is going to be compact, but compact means closed and bounded. But then since this interval is connected, that means its image is going to be connected. But then if you've got a set that's closed, bounded, and connected within the real line, you can prove, maybe via a nice exercise, that that set must be itself a closed interval. So anyway, that's how we get this result right here, which is in fact extremely close to the extreme value theorem that you learned in calculus. All right, so I want to finish this video off with a nice proof that the real numbers are uncountable using topological methods. All right, for our last result, we need a bit of a definition. So let's say that x, a point x inside a topological space x, is an isolated point if the singleton containing x is an open set in our topological space X. So as an example, let's say that our topological space X is the closed interval from 1 to 3, union the singleton 4, union the interval from 5 to infinity, including 5. And let's give this the subspace topology where we take the standard topology on R. Now let's notice that the singleton containing 4 is equal to the open interval from 3 to 5 intersected with x. Notice this does not include 3 or 5. That's how we only get that singleton 4. But since it's going to be our topological space, our subspace I should say, intersected with an open set in the parent space, that means that this singleton 4 is open. But since that singleton 4 is open, that means that 4 is an isolated point. But just thinking about the picture, if you will, of this set X, notice that this definition encapsulates kind of exactly what we would want for an isolated point, given that this set X looks something like this right here, and there's our point 4. That is definitely like isolated, if you will, from all the other points within the space. Now we're going to prove the following theorem. If we've got a set which is compact and it's non-empty and it's Hausdorff, then if there is no isolated point, our set must be uncountable. So let's observe that the converse of this is not true. And we can see that the converse of this is not true simply by, well, not our example right here, but perhaps a cutoff version of our example. What if we just consider these two things right here? So the interval from 1 to 3, closed interval from 1 to 3, and the singleton 4. So let's observe that that's most definitely compact because it's closed and bounded and it's a subset of the real line. It's non-empty, and it's Hausdorff. But let's observe that it has an isolated point, and yet it's also uncountable. So notice that that shows us that this converse is not true, because the converse would be uncountable implies has no isolated point, but that's not what we have here. Okay, so let's get going with this proof. So let's start by taking any non-empty open set, so I'll call this open set U, and it's going to be open in our space X, and any point little x within X. Okay, and then let's note the following. We know that U cannot be equal to the singleton containing X. We know that because X has no isolated points. And if U was equal to this singleton, then this singleton would be open, but then by our definition over here, that means that we would have an isolated point. Okay, So since u is not equal to this singleton, then there exists some point y inside of u such that x is not equal to y. Okay, now we've got 2 points inside of our topological space x. Now we'll apply the Hausdorff condition. So that means there exists open and disjoint Vx and Vy with x is inside of Vx and y is inside of Vy. So again, that's the Hausdorff condition. Now, what are we gonna do from there? So now what we'll do is set W equal to u intersected with Vy, and let's observe that this W is non-empty. So how do we know the W is non-empty? Well, it at least contains y. Well, since it's open, it's got to contain more of y because we don't have any isolated points, but it at least contains this point y. So it's non-empty. And I'd like to leave a tiny homework exercise here, and that homework exercise is that x is not only inside of W, but x is not inside of W bar. Okay, great. So now I want to stop for a little bit and notice the construction procedure that we have just built. And that is, we've been able to start with a point x and an open set u, and we've been able to construct a new open set w of x such that w satisfies two things. W is a subset of our original u by this line right here, and x is not inside of W bar. Okay, so now let's see what we can do with that construction. Okay, so we've just built this construction that does the following. It takes an open set of x and a point inside of x, and it constructs a new open set W, which is a subset of u, where the closure of W does not contain x. And now we'll use this to prove the uncountability. So now let's suppose that we've got a function from the natural numbers to x. And from this function, let's create a sequence. So let's set x sub n equal to f of n. Notice that these are all going to be points within x. And now let's step back a little bit. And let's observe that if x were countable, then it would be possible for this function to be onto or surjective. But if x is indeed uncountable, we should be able to prove that this function is necessarily not surjective. And that's exactly what we're going to do. And we're going to do that by applying the construction iteratively to some things built out of these points x, n. And maybe we'll lay this out in a chart right here. So for the first round, we'll take our set u to be the entire set x, and then we'll take our point x to be the point x1. And notice out of that, we're going to get a set which we'll call w1 within x. And for the first round here, we're going to take our open set to be the whole set. We're going to take our point to be x sub 1. And now let's observe that out of that, we get an open set which we'll call w1, which is a subset of the whole thing. And x1 will not be contained within the closure of w1. And now, well, the idea here is just to keep doing that, but starting with the open set that we ended with before. So now we're going to start with w1 and the point x2. And that's going to give us a w2 inside of our w1, and we'll have x2 is not in the closure of w2. And then doing it again, we'll start with w2 and x3. That'll give us a w3 contained within w2, and then x3 will not be contained within w3 bar. And then, well, we're just going to keep going and going and going. And at the general step, it'll look like this. we'll have our set Wn minus 1 and our point xn, and that'll allow us to construct a Wn, which is a subset of Wn minus 1, where xn is not contained within Wn bar. Okay, so now let's see what we've got here. We've got this collection of closed sets. W1 bar, W2 bar, W3 bar, so on and so forth. And it's in fact an infinite collection of closed sets, and they're all nested in fact. Notice we've got the following nesting. So here, over here we've got x at the end, and we have W1 bar is contained within x, W2 bar is contained within that, W3 bar is contained within that, and then a general term down here will be Wn bar. And then let's look at a finite intersection of these, because what we want to do is at some point use this finite intersection property and our compactness. We haven't used compactness yet. But let's observe that any finite intersection has the following form. Wn1 bar intersected up to Wnk bar. But then by the nestedness, that's going to give us the smallest of these sets. And so we might write that as W capital N bar, where our capital N is equal to the maximum of these little n's. I think that's pretty clear just by the fact that this thing is nested. And then notice that this W capital N bar is non-empty. And that's because of our construction property, our W was non-empty. I don't have that written here, but let's maybe go ahead and put that in there. Our W is non-empty. Okay, so now, well, what does that mean? So that means our collection, which I'll maybe call Wk as k runs through all natural numbers, has the finite intersection property. But since it's a collection of closed sets with the finite intersection property, and we are within a compact space, that means that the intersection of all of them is also non-empty. So that means this intersection, k going from 1 to infinity, or k over all natural numbers of Wk, is non-empty. Okay, now, well, where can we go from there? Well, two things are true, and these two things are really important here. And that is that x sub n is not inside of Wn bar for all n. But that means that x1, x2, so on and so forth are not elements of this intersection because they're not in the set that is related to their index. But then that together with the fact that this intersection is non-empty means that there exists an x inside of this intersection which is not equal to any of these xn's. Okay, but then that tells us that the image of our set x, but then that means that the image of the natural numbers under our function f is not equal to x. In other words, f is not surjective. Okay, good. Now let's take a step back and see what we've done here. We started with an arbitrary function from n to x. And through this argument, we showed way down here that it is impossible for f to be surjective. But if it's impossible for f to be surjective, then it's impossible for f to be bijective. But what defines countability? Well, a set is countable if and only if it's in bijection with the natural numbers. We just showed that it's impossible for x to be in bijection with the natural numbers, meaning by definition, x is uncountable. And now let's observe as a quick corollary that the closed interval from 0 to 1 is uncountable. That's because the closed interval from 0 to 1 is compact in Hausdorff. But then the closed interval from 0 to 1 is a subset of the real numbers. That means that the real numbers are also uncountable. And there's a nice topological argument that the real numbers are uncountable. Okay, so now I'm going to leave you with some homework exercises. All right, so here's some exercises based off what we just saw. So let's prove that a subset of Rn is compact if and only if it's closed and bounded. Next, let's prove using a compactness argument that the closed interval from 0 to 1 is not homeomorphic to the open interval from 0 to 1. And then finally, let's suppose that we've got a collection Ki of closed compact sets. Then let's show that the intersection of this collection is also compact. And that's a good place to stop.